specific indicators or bacteria to know where there's a human fecal contamination event. In this case, what they have are the fecal indicator bacteria, and these are Enterococcus species. And through a series of studies, they identify a specific threshold, in this case, 70 colony forming units per 100 milliliters. And what this means is that whenever we exceed that specific concentration, it suggests a public health risk. The specific effect, and this is one example, all gastrointestinal diseases. And there was a study in 2012 in Puerto Rico by Cordero and others. And by looking at an area that had this high concentration of these indicators, that had a fecal pollution contamination from humans, they found that about 5 cases per 100 bathers, 5 people were getting sick per 100 bathers. Now that we know a little bit about these 2 pathogens, mosquitoes and water-related, in this case, Enterococci, there have been studies showing how the environment can actually influence the variability of both mosquito-borne diseases and water pathogen diseases. And in this case, I'm going to be just summarizing some of these studies, and they were mostly done in short-term times. If we have a coastal area and you have high temperatures have been correlated with an increased activity of bacteria in the water, as well as most mosquito-borne diseases. Also, high temperatures can lead to evaporation, cloud formation, and it's going to increase the amount of precipitation potentially in a specific area. When we have precipitation, what we think is specific particulate matter. This particulate matter can be associated as well with viruses, pathogens, and bacteria. And through increased rainfall, we have runoff, what is going to lead to turbidity and more turbid waters, also correlated with high fecal pollution and other viruses into the water. But not only that, when we look at the sediments and the sands, we also have those viruses and bacteria there as well, and they can survive there. And if we have specific high energy events, like windy events or more waves, we see all of this being resuspended, creating more turbid waters and increasing the concentration of specific pathogens. If we go back to precipitation and we think about mosquito, as part of the mosquito's life cycle, they need water. They need stagnant water to be able to leave their eggs and larvae to grow. So by having more precipitation, we have more breeding sites for these mosquitoes. And by having more breeding sites, it's going to lead for higher activity of mosquitoes, leading to more people getting bitten and a potential spread of a specific disease. Let's just say, for example, in this case, dengue fever. By knowing this specific relationships between some environmental factors and specific pathogens, the overarching question for my dissertation is to look at how large-scale environmental parameters can influence mosquito-borne and water-related pathogens in specific locations in the tropics and in a more long-term area using oceanographic parameters, as Frank mentioned earlier. In order to answer this question, what I did is I divided my dissertation into 4 main objectives. And the first one is looking at modeling dengue fever incidence using regional scale satellite-derived sea surface temperature. In the case for this objective, I look at the northwest coast of the Yucatan Peninsula and is working with these 8 municipalities shown in here. And for Mexico, thousands of dengue fever cases have been reported annually since the 70s. And this is very true for the rest of the America, including some part of the US. For the Yucatan state, we saw an increase of 45% in number of cases of the dengue cases from 2014 to 2015. And this is very true for this specific year. However, it could vary in other years or in other locations. It could be higher, less than that. And it's very related to the epidemics and to the phenology and how the virus and the mosquito behaves themselves. And lastly, some of these studies in Yucatan have been looking at those potential breeding sites, that stagnant water that I mentioned earlier, and how can that affect the spreading of a virus. And there have been other environmental parameters that have been also used, And in this case, these studies have been looking at El Nino and how El Nino can influence dengue virus in Mexico. And by doing so, they've been looking at sea surface temperature, but the sea surface temperature that they looked at was from the Pacific Ocean, the one that is more related to El Nino. So knowing this and knowing that there's some sort of gap between what they were doing and more regional scale type of data, what I did to be able to understand this relationship was I took the time period from 2007 to 2012, and I used a combination of satellite-derived data, such as sea surface temperature, shown here, with in situ collected data, such as air temperatures, humidity, and precipitation. The first thing that I did with this data was I used a series of linear correlation analysis to be able to understand the time lag between environmental variables and a change in environmental variables with a change in dengue fever cases occurrences. After identifying these time lags, I use an AIC model selection, which is an archaic information criterion, to identify those variables that would substantially contribute to explain dengue cases. And after identifying those variables, I put everything into a multiple linear regression model to identify how much of the variability was being explained only by environmental factors. This is part of the results, and this is kind of a lot, and I'm going to be walking you through it. So from top to bottom, what we have is all of environmental variables: humidity, sea surface temperature, air temperature, minimum, average, and maximum, as well as precipitation, and all the way to the bottom, dengue fever incidences from 2007 to 2012. And as an example, if I show you in terms of the patterns of all of these variables and dengue fever, if we look at 2008, we see that when we have a decrease of all of these variables, they're significantly correlated with a decrease in dengue fever cases. And it shows you how cyclic dengue cases can be throughout the year. So they follow all of these environmental variables. In terms of the green bar over here, when we have an increase of all of these variables, there's an increase correlated with dengue fever cases. However, it's a little bit off, and this goes back to the time lag that I was calculating earlier. And to give you an example, and since sea surface temperature is the most important variable for my objective, in terms of an increase in dengue and an increase in sea surface temperature, there's a time lag of about 5 weeks. Continue talking about sea surface temperature. I wanted to know, the main objective was to know how much of the variability can also be explained by just looking at that variable. And by using a linear regression model, it was found that 26% of that variability was explained only by sea surface temperature. Regardless of this, I put all of these variables into the AIC selection model to know which one of them were the most important ones and how much of the variability was being explained. And by doing so, the model identified these 4 variables to be the most important ones: minimum air temperature, sea surface temperature, humidity, and precipitation. And by using a combined model with all of the environmental variables, it was able to explain significantly 42% of the variability. In terms of a summary for this first objective, this study indicated that using regional scale, satellite-derived sea surface temperature can really help you model dengue fever, with that 26% being explained by that variable and it being included into the most important ones. Also, that the combined environmental parameters can explain almost 50% of that variability of dengue fever. That other 50% could be mostly explained by human population or for susceptibility for the specific virus. Regardless of that, only environmental variables were able to explain a higher amount of the variability. And finally, that remote sensing should be considered for future efforts to improve the prediction and mitigation of dengue fever. And in this case, we can see that with satellite data. And also, if we are better able to understand dengue fever variability, we might be able to better predict other diseases such as Zika virus, chikungunya, because they are being transmitted by the same vector, which is the Aedes aegypti mosquito that I showed earlier. For the second objective of my dissertation, I look into evaluating bathing water quality in the context of specific environmental parameters. For the purpose of this study, I look at Escambron Beach, located in the municipality of San Juan, Puerto Rico. And this is looking back to the EPA and those specific indicators, fecal indicator bacteria that they use to identify fecal pollution. And these are cultural enterococci. And I also look at the specific beach action value, which was the threshold they identified that suggests a public health risk. The reason that I say that it only suggests a public health risk is because you need to have a specific source of human fecal pollution known to be able to correlate that with your indicator bacteria identified by the EPA. And also there's the fact that Enterococcus species, they can vary a lot. We have our human sources of Enterococcus species, which are actually a threat to public health, but we also have animal sources. It could be bird poop that not necessarily are considered a threat to public health. And then we have all of these environmental parameters that can influence the variability and concentrations of these bacteria. And there are gaps between understanding how the bacteria can change depending on environmental factors and whether or not that's going to lead to a public health concern. In order to understand that, I took the time period of 2005 to 2015, and all of my environmental variables are again a combination of satellite-derived data and in situ collected data. And in this case, my satellite data is sunlight, turbidity, and sea surface temperature, where rainfall and sea level were in situ collected. The first thing that I did in order to understand these correlations and relationships, I divided up this environmental data into specific ranges. And the reason behind this is to better understand how specific characteristics of these environmental parameters can influence the concentration of these bacteria and whether they're going to cross that BAV value that suggests a public health concern. And I did a series of ANOVAs to be able to understand significant difference between these bins. After doing that, I used a similar AIC model selection approach to identify which one of those variables were the most important ones or substantially contributing on explaining cultural enterococci, and then the multiple linear regression model to assess the significance of this. In terms of the results, this is only a snapshot of all the work you do here. So the first part, the first graph here, what I'm showing you is the cultural enterococci mean, geometric mean concentration, plus minus the confidence intervals. And all of the x-axis are going to be those specific ranges of these environmental factors. In terms of the first one, precipitation, what was found was that between 481 and about 960 millimeters of precipitation, concentrations of these bacteria were crossing that threshold, suggesting a public health concern. Whenever we had lower than that, it could potentially mean that we don't have enough source of the bacteria. Whenever we have an amount higher than that range, it could be that everything is either being diluted or completely washed off, and again, we don't have a lot of bacteria in the area. In terms of irradiance, and this is just the amount of sunlight it's receiving to a specific area, what was found was that with lower amount of irradiance, we see that the concentration of the bacteria was above that threshold, suggesting a public health concern. Whenever we have more sunny days, we see that the concentration is well below that, so it's safe for people to go swimming. Basically, if it's sunny outside, it hasn't rained, you're good to go, you won't get sick. And this lower irradiance having this relationship, it could also mean that it's cloudy and it's related to the amount of precipitation that I showed earlier. In terms of turbidity anomalies, this is looking at the water being more turbid than average or less turbid than average. And with higher turbid waters, what we see here is the potential to cross that threshold, suggesting a public health concern. And this goes back to part of the introduction that I provided, that turbid waters are correlated with high concentration of these pathogens. And this could easily mean that the actual turbid particles are the source of this, or the turbidity is just protecting the bacteria from the UV light that we saw from the irradiance. And finally, when we have sea surface temperature anomaly, just warmer than average or cooler than average, it didn't really cross that BAV value, suggesting a public health concern. However, when you look individually at each one of these bins, you can see that the concentration of the bacteria is significantly increasing, which could lead to crossing that threshold and suggesting a public health concern in this location. After doing all of this to look into all of these environmental variables individually, I put all of them into the AIC selection model. And this model identified these 5 variables shown here: precipitation, mean sea level, irradiance, sea surface temperature, and turbidity as the most important ones. And the combined environmental variables were able to significantly explain 20% of that variability. The missing 80% of this could be more related to more human activities and infrastructure in the area that are influencing the concentration of the bacteria for Escambron Beach. In order to look more into satellite images, I selected the March 9 of 2007, and the reason of this was because the concentration of the bacteria was above that BAV value, suggesting a public health concern. So I looked into turbidity because it was already shown that turbidity is correlated with high concentration of bacteria, and I mapped March 6 to March 8 anomalies of turbidity and did an average for those days. And in here, what I'm showing you is red areas are higher than average, blue areas are lower than average, white is just average, and gray areas are missing values. And the study area is shown here in the yellow box. And what we can see here is that it's all red. So knowing that it's all red, we have higher than average turbidity anomalies, which is also correlated with high enterococci concentration. What we can do with this is, I have this information, it's higher than normal, it's a potential public health concern. What can we do to protect human health in this area? So this is basically to show how satellite images can look at the spatial distribution of specific parameters and use them in potential early warning systems for the area. As a summary for this part of the dissertation, all I did was look into specific environmental factors, put them into a multiple linear regression model, and just environmental variables were able to explain 20% of the variability. Also, by separating this into individual ranges, it was found that for Escambron Beach, with warmer waters and more turbid waters, it led to high concentration of enterococci. Lower irradiance led to high concentration of enterococci. And with precipitation, it was specific values, specific ranges that led to high concentration of enterococci. All of this suggesting a public health concern for this specific area for this time period. And lastly, how satellite-derived data can help assess spatiotemporal variability, like it was shown with the turbidity image, to better understand what is going on and to develop early warning systems. For the purpose of the next 2 objectives, I use a predictive model. And for the first one, I look into predicting dengue fever outbreak occurrences based on specific population segments in Mexico and Puerto Rico. In order to do this, the models that I used were artificial neural networks, and this was developed by our collaborators from the University of Exeter, including one of my committee members, Dragan Savic, and one of his students. And they provided this to us where we adapted the model to be able to predict dengue fever outbreaks in the municipality of San Juan, Puerto Rico, shown here, and then the northwest of the Yucatan Peninsula, which take us back to the 8 municipalities that I used in my first objective. In order to provide a little bit more public health type of background for understanding these issues, dengue fever has 4 serotypes, and these are distinct variations within species, and it's more related to the surface of the cell and how they identify this. They have dengue virus 1, 2, 3, and 4, and they have more recently discovered a fifth one in terms of differentiating all of these virus types. One of the reasons that I mentioned this, it's because it's very important to understand which one of these serotypes is circulating. Because you can have 1 and 2 circulating for a certain amount of time, and the people that is exposed to that could create some sort of immunity or partial immunity to this type of viruses. But then after so many years, when there's a shift from, let's say, 1 and 2 to 3 and 4, people are still susceptible to getting dengue virus and to become infected. And these tend to lead to epidemics. And these epidemics tend to be more than 10,000 cases. So if we think back about Puerto Rico only having 150-ish cases, US having 760, and then Mexico having 17,000, think of these numbers to just go way over 20, 30, 40,000 for specific areas like these. In terms of the model, I'm going to be showing you like the basic structure of this model to give you an idea what it was doing. It has an input layer, and this input layer consists of all of my variables, all of the variables that I wanted to use to be able to predict my outcome. From that input layer, it goes to the hidden layer, and by doing so, it calculates a series of weights, and these weights are looking at the magnitude of the relationship of inputs towards the outputs. After the hidden layer, it has the next step, and in this next step, it calculates another combination of all of these weights, similar looking at that influence of inputs to outputs. And then finally, we have our output layer, which is our prediction. And by getting that prediction, it has a W0 shown here, which is a combination of W1, W2 through matrix math, and we get our final influence of inputs to outputs. If I populate all of this information, I show you all of my input variables, which are, again, a combination of satellite-derived and in-situ collected data, which are sea surface temperature, precipitation, population size, air temperatures, and previous dengue cases. By previous dengue cases, when you look at studies in epidemiology, they tend to use these previous cases. You want to know what's happening in the area and the potential to that virus or disease to spread. So by looking at 1 week, in my case, is a week before, the average of the week before number of cases, it gives you an idea what's going to happen next. Are they going to keep increasing? Are they going to decrease? And why that's going to happen. And then my output layer are the predictions for dengue fever occurrences in these 2 locations. In terms of the data, Puerto Rico, I had 19 years of data, and for Mexico, there were available 6 years of data. What the model is doing, it's looking at the combined neural pathway strength analysis. That's the full name for that, basically W0. So in simple words, what it's doing, it's looking at the influence of the inputs on outputs in terms of the magnitude of that influence to identify which one of these variables is the most important one. The predictive capability of these models were measured using the receiving operated characteristic curve, which is AUC, area under the curve, and this is looking at the ratio of true positive and true negative, and wanting to have more true positive because we want to have a correct prediction. And finally, these models were divided by 2 population segments. Those are younger than 24 years old, and those are younger than 5 and older than 65. The reasoning behind this is when you look at the data, you tend to see different peaks in terms of number of cases. Those that are younger than 24 are more exposed to the virus. We're more outside, we're more at risk that a mosquito comes and bites us and we get infected by the virus. Those that are younger than 5 and older than 65, it could be more related to their immune system. Either they're developing their immune system younger than 5, or your immune system tends to become compromised when you get age. And it could be a little bit more tricky than that because immune system, it's more complicated than just saying that as we get old, it gets compromised. But this is the idea behind all of these age groups. And there's an overlap between younger than 24 and younger than 5. And the reason And the reason behind this overlap, it's because even though they're younger than 5, they might be more vulnerable, but they still, if you have a kid and they're playing in the backyard, they're still considered at risk and exposed to get bitten by a mosquito just playing outside. In terms of looking at the specific weights and the magnitude of the relationship between inputs and outputs, and I'm going to be walking you through these graphs. The first one, what we have here are the 2 models for Mexico. The first column are less than 24 years old, younger than 24 years old, and the second columns are younger than 5 and older than 65. In order to populate this, our y-axis is our W0, that influence of inputs to outputs. The x-axis are going to be all of that input variables that I used. And I just wanted to let you know that all of these variables are in order of the most influential to the least influential to predict dengue fever in this area. These are all the weights. And just to summarize the results of this part of the objective and these first 2 models, for those younger than 24 years old, the model identified 5 variables to be the most influential ones. And these are a combination of demographics, which are population size and previous dengue cases, and environmental variables, which include sea surface temperature and air temperature and precipitation. All of these variables are well correlated with what they do to number of cases, whether they impulse to them increase or decrease. In terms of the younger than 5 and older than 65, only 3 variables were selected by the model. And these variables were only demographics, population size, and previous dengue cases. But it actually selected date. And the reason date is included here, it's because of that cyclic pattern that I mentioned on my first objective, that you always going to have that dengue fever cases taking place at the same amount of the year, but that magnitude is going to change. And this is more related on the immune system of the population and the serotype that is circulating. There are many other reasons that it could change. But overall, every time, the same time of the year, you're going to have dengue fever cases, most likely because it follows all of these environmental parameters, cyclic patterns of the environmental parameters. In terms of the predictive capability of these models, the one for those younger than 24 was 88%, and the ones younger than 5 and older than 65 was 90%. And this is again looking at the ratio of true positive and true negative and how certain our predictions were. For Puerto Rico, I have the same organization of the data, where the first column is my model for younger than 24. The second column is for younger than 5 and older than 65. And to summarize again all of this data, the model for those younger than 24 years old identified only 4 variables, which were very similar to the one for Mexico, and are again a combination of demographics and environmental variables. The environmental variables are sea surface temperature, are air temperatures, and the demographics, population size, and previous dengue cases. And we have date, again, being identified as one of the most influential ones. In terms of those younger than 5 and older than 65, for Puerto Rico, it was a little bit different because it identified demographics, similar to Mexico, population size, and previous dengue cases. However, it also identified maximum air temperature as one of the most influential one, which we can also see in the younger than 24 years old. And there have been previous studies shown in Puerto Rico that maximum air temperature is correlated with high number of the mosquito bites. And this could be to many reasons: warmer, more activity, more metabolic activity, they get hungry more often, they bite people, and so on. In terms of the predictive capability of both of these models, the one for younger than 24 had a 91%, and the one for those younger than 5 and older than 65 had a predictive capability of 71%. In summary, for this third objective, what it was found, or what this is showing, is that by using nonlinear modeling, in this case artificial neural networks, we show a high predictive capability for dengue occurrences or dengue fever outbreaks in Mexico and Puerto Rico as well. that the demographics are really important to take into account when you're doing this type of predictions, and that the model was able to take this holistic approach to identify what combination of environmental variables with demographic variables would be the best ones or had the highest influence to predict an outbreak of dengue fever for these two locations. And lastly, that the pathogen phenology, and by phenology what I mean is how the pathogens behave throughout the year based on the climate or the ecology of the pathogen itself, is better assessed with specific population segments. And in this case, I'm referring to younger than 24 and younger than 5 and older than 65. However, we do still have that overlap between younger than 24 and younger than 5. And there are some limitations when doing this type of work. And it would be very important, or it would be most helpful to identify the immune status of this population to be able to better predict what's going on and divide these population segments. For the last objective of my dissertation, I look at identifying the most influential environmental factors to predict bathing water quality exceedances. And in this case, we go back to Escambron Beach in San Juan, Puerto Rico. And we're talking about an area that has a swimming season of 365 days a year. So basically, you go to the beach every day. It doesn't matter what season is. It has a tropical climate, like I was mentioning, and this is very important to know, especially when you're looking at specific pathogens in water, because you want to know how they may or may not behave depending on this climate. And then between May and September, mostly the residents from the municipality of San Juan are the ones that visited this area. Outside of this time period, it's people from around the island or outside of the island. And the reason I'm mentioning all of these points, it's when you're doing this type of public health related work, you need to know who's going there, who's susceptible, who might be exposed to all of these things. And also, they're the ones that are going to be most interested in the results of the type of the research that you do. In terms of the artificial neural network model, this is the same structure that I showed you earlier. And if I populate all of these variables into my model, we have sea surface temperature, turbidity, dew point, irradiance, mean sea level. And in this case, I use cumulative precipitation from 24 hours up to 120 hours. And our predictions are exceedances, which are the culturable enteric oxide exceedances, meaning that identifying when they were above a set threshold. For this part of the project, I had 11 years of data. The threshold was the 70 coloniform units identified by the EPA that suggests a public health concern. And again, it's using the combined neural pathway strength analysis, where it's looking at the influence in terms of the magnitude of inputs towards outputs. And the predictive capability was measured using the area under the curve. In terms of the main results of this model, we have all of our weights in the y-axis. X-axis is, again, all of the input variables, which are organized from most influential to least influential to predict cultural enteric oxide for this location and time period. And just to summarize what we're seeing here, the model identified 5 variables to be the most influential ones. And these were a combination of irradiance, turbidity, 48 hours of cumulative precipitation, mean sea level, and sea surface temperature. And this goes, again, to the relationship of all of these environmental parameters to influence cultural enteric oxide variability, or higher or lower concentrations. In terms of the predictive capability of this model, it showed a 74%. As a summary for this last objective, the most relevant parameters were identified, which are these 5 that I just put here again for all of you to see. And what I want to mention here is that the first 2, irradiance or turbidity, are from satellite-derived data. This is data that we don't actually go collect every time we do sampling for cultural enteric oxide. So it's very important that we have this satellite-derived data so I can go back in time to be able to understand variability from the late 90s, early 2000s up until now, and better understand what's irradiance or what's turbidity doing in terms of identifying all of these concentrations. Without any of this, all that we usually have is precipitation because it's collected mostly in situ and it's one of the cheapest ones to be able to collect. In terms of the predictive capability, the models, the nonlinear models, artificial neural networks showed a 74%, which tends to be higher than most linear models. And this is not comparing this with what I did earlier. This is comparing this with other studies have been done outside of the tropics. I know many studies have been done using artificial neural networks to understand how these variables in a nonlinear way are correlated with cultural enteric oxide. And finally, and this is just reiterating what I just said, better predictions can be achieved with satellite-derived data. Thanks to satellite-derived data, we can do more long-term type of studies since the data is available there since the 90s, and it helps us understand and predict more human health-related type of studies like mosquito-borne and enteric oxide. In terms of concluding my dissertation work, satellite remote sensing provide very useful data for vector and water-related pathogens and can be used for early warning system as shown in my second objective. And even though we as oceanographers, we tend to use satellite data and a lot of this data every day, most of us, when you go to the public health or microbiology long-term studies, it's more like a novel approach. So how can we better communicate with this other community so we can all talk in the same language? We can tell them this is very useful because we can do all of this stuff. In terms of the mosquito-borne diseases, because of that ocean-atmosphere interaction, we can use sea surface temperature in many other places to be able to model dengue fever and come up with better management strategies, especially when we have those diseases coming up like Zika virus, chikungunya, more like Zika virus, and all of those outcomes that we see with microcephaly and all the worries that that creates in all of the population around the world. And that we can achieve spatiotemporal assessment regarding bathing water quality. I only showed you an example with turbidity. We can do the same with many other parameters looking at specific anomalies, and that can help us better understand what's going on in the entire area and how can that affect the study area or the entire coastal area of a specific location. And lastly, when you combine all of this with nonlinear modeling, in this case I use artificial neural networks, can help improve predictions of health-related matters. And by health-related matters, what I mean for my case was mosquito-borne and water-related pathogens. And I mentioned the tropics, but this can actually be expanded to other different areas around the world. In terms of the next steps and some of the limitations of this work, by using artificial neural networks, all I did was prediction. All I did was predicting what's already happened there. It would be good to modify these models to do more forecasting and nowcasting of these diseases to see how helpful they can be to reduce and mitigate what's going on. Also, serotypes are very important. They're very expensive to get the data. Not everyone can do that, but just to get an idea how serotypes are changing, it can provide us better predictions and also human population movement. And I mentioned this, I don't know if all of you remember, when we had the Zika outbreak, when we started having Zika outbreaks in Florida, it was because someone traveled to a place that had Zika, came here. If a mosquito bites you with the virus, the mosquito Aedes aegypti is here, you can spread the virus. So taking into account human population to do these predictions might be really, really helpful or more helpful to better understand what's going to happen with these diseases. In terms of the fecal indicator bacteria as health indicators, as I mentioned, we need to know those human impacts. We need to know if there's a source of that fecal pollution to be able to correlate it with those specific pathogens and with the environment and with public health concerns. If there's not that specific source, that correlation might not be there, and that might be an issue to better understand health concerns. Regardless of this, we still follow the EPA guidelines because we have this indicator correlated with human health concerns in specific areas. And going on this, I'm part of an ongoing research, which is MERA. It's Environment, Ethnography, Risk Assessment, and Water Quality done in Costa Rica. This is a combination of USF Tampa, where Dr. Harwood and Maya Braver are part of this, and Erin Simmons. And what they're doing is, this is mostly expanding my microbial water quality work. What they're doing is assessing specific pathogens related to human impacts. Once we see these pathogens, we can correlate the pathogens with the indicators that they're actually assessing, and I have all of the satellite-derived data, and everything for Costa Rica is from the satellites, to be able to understand relationship with that, assess health-related issues with fecal contamination, and potentially develop a early warning system with something that it's already in place in Costa Rica with their collaborators. With this being said, I'd like to thank all of my committee members for all of the input, suggestions, and all of the support through all of these years. I want to also thank all of my collaborators that they helped me get data, understand data, analyze data, and publish most of my dissertation. And I also want to thank my group of people that helped me and gave me support through all of my years as a Ph.D. here in the College of Marine Science. Last but not least, I want to thank my funding agencies because they gave me the support to be able to finish this. And I also want to say thank you to my parents that are here, that they're actually here with me for their all support since day one when I started my degree in Puerto Rico. With that being said, that's all. Thank you. Yeah, sure.
So I have a question, a couple of questions about your first part of your project.
Mm-hmm.
So you showed that the 4-parameter regression model did better than the single variable regression model with sea surface temperature.
Mm-hmm.
Did you test the pairs to show that? Because I would suspect that you probably could find 2 pairs that did almost as well as all 4, because 3 of those variables are so highly correlated.
Mm-hmm.
So did you do that test, and what were the results?
I actually can't say that I did that specifically, but the way the model that I used to identify those variables, it was looking at different combinations of these variables to see what you just said, and then provided me the ones that were significantly contributing to what I was seeing with dengue fever.
But you don't know, like, if precipitation and SST explain 41%.
It provides me a table with all of those R-squared variables that I have towards the end of all of this. That it gives you an idea of how much of the variability was being, cumulative variability was being explained by each one of these variables, which is here. So it will give you all of this and see the cumulative precipitation all separately. I don't have it here to show you. It gives you an idea of how much they can contribute to explain what we're seeing.
That's not.
Oh, sorry. That was the wrong one. In case you had a question for that one too. I believe this is the one. There you go.
There's actually not a big difference.
It isn't a big difference, yes. Mm-hmm.
All right. And it might be
I'm sorry.
interesting to kind of redo that in a different order as well, because you might find one is better. The other question I had is on that test.
Mm-hmm.
Did you look at if it was just predicting the seasonal variability aspect well and not the interannual? Because I also suspect, because there's a lot of seasonality
Mm-hmm.
in a lot of those environmental variables, that a lot of your predictive capability is for predicting the season, and it might not do the interannual as well. Did you consider that at all?
The only one that I tried to remove that variability was sea surface temperature, looking at anomalies of sea surface temperature. The other ones, I can say that I tried that. Probably because sea surface temperature was the main one that I was looking at, but I didn't look at that. But that would be,
And
yeah.
with sea surface temperature, did it explain less of the variance when you removed the sea
The 26%. All sea surface temperature in here, I didn't identify it, but I'm looking at anomalies of sea surface temperature. All of that for the
By
project.
anomalies, you mean you've removed the seasonal climatology?
Mm-hmm. Go ahead, Maria. You? Yeah, you.
I guess my question is kind of related to things, and it's that in chapter 1, you kind of state that sea surface temperature is like the main driver. Right?
One of the good ones to
Right,
predict dengue
you kind
fever.
of
Yeah.
highlighted sea surface temperature.
Mm-hmm.
But then in chapter 3,
Yep.
you kind of mentioned that air temperature was kind of the main driver for disease outbreaks for the population under 24 years.
Mm-hmm.
So what does that mean in terms of disease outbreaks?
In terms of the disease outbreak,
Like if I were to manage that area, would I be more concerned with temperature or like air temperature or sea surface temperature? What would I be more concerned with?
I mean, I would think they're kind of correlated to surface temperature and minimum air temperature in some way, that connection between ocean and atmosphere. But it might be easier to and better to look at the air temperature in your location, especially minimum air temperature, because it's the most important one. And I would look at that, if that answered your question or not.
So for population, people under 24 years exposed to whatever
Dengue
virus,
virus.
air temperature, yeah, so that.
The way the model it identified that, it puts minimum air temperature before sea surface temperature. Even one of the models just kicked out sea surface temperature, actually.
I think it was the
So,
same one that I'm talking about, so
Mhm.
that's why I was kind of.
yeah. So what I think here is, because we're looking at the the nonlinear approach to better understand those complex relationship, maybe what sea surface temperature was doing, because of that cyclic pattern that it always have or something, was being more heavy on the linear model. And once I look into the nonlinear model, demographics and all of the other ones showed what they were actually doing. That makes sense.
Follow
sorry.
up on temperature.
Yeah.
Part of the time it looked like it was a positive correlation, part of the time it looked like it was a negative correlation. Well, the minimum temperature
Okay.
was a positive correlation, I
Mhm.
put it that way. And other times, if I was reading it right, that there was a positive correlation with maximum temperature.
Mm-hmm.
And I think the difference may have been between Mexico and Puerto Rico. But certainly I noted that there was a minimum, the correlation with minimum temperature was in the data from Mexico. Would that be accounted for as a covariate of cloudiness and essentially irradiance, the low irradiance, high would be a cooler temperature? I'm trying to figure out why sometimes you've got a negative correlation.
With temperature.
Negative correlation with temperature. And
And this is regarding the model, the predictive model, or because the nonlinear ones showed only positive in general. So
the data.
the only reason that I could see a negative correlation between temperatures and disease, it's the range the mosquito can stand to survive in terms of temperature. If it's too warm, it's not gonna be too good for the mosquito. If it's too cold, it's not gonna be good. You're between this range. And that's why it's very good in the tropics, because we actually have that range for the mosquito. So if we have a negative correlation, it might be more related to the mosquito itself, and that might be a negative correlation with my cases, because there's a gap between what the mosquito is doing, biting people, people getting infected, reporting the cases, and that's what I have. So does that answer your question?
That answers it perfectly.
Okay. I think, yeah.
I have two quick questions, and neither one of them is about precipitation. So in your second chapter, towards the end, you mentioned something about the missing 80% of variability,
Woo.
and you said really quickly that it was maybe human activity, and I was wondering if you could just explain that a little bit
So
more.
by human activities, what I mean is infrastructure. wastewater treatment facility discharges that I couldn't account for, bathrooms, this specific area, there's no map there, this specific area, this specific area has bathrooms really close to the beach, and there are leaks, and all of these things I couldn't account for. So maybe there was a peak or a decrease that didn't really, the environment influence on that, and that's probably I got 20%, and that 80% could be related to that. Or the actual ecology and biology of the bacteria, how it behaves naturally in the environment and predators and so on and so on.
Okay, and my other question, thank you. My
Yeah.
other question, kind of a lot of the data that you presented had a lot of variability, and I think specifically it may have been the first chapter, your results. I think it was the first chapter, the kind of the line, the EPA kind of critical, threshold. A lot of your means were above that line, but the bars, like the differences the groups weren't statistically different, right? And there was a lot of variability. I'm just wondering if
This?
Yes, and there was some variability for your other data points too. I'm wondering if that variability is actually attributable to the natural variability, the natural ranges of these data points, and I'm not, familiar with a lot of these variables, or if it's an artifact of your data set, like how many data points you had, or, I guess asked another way, if you had more data points, would you expect that variability would shrink and maybe those, it would be tighter and maybe the differences would be statistically significant?
I would actually, if I had more data point, it might go a little bit down the variability, not much, just because cultural enterococci in this case, it can vary a lot. It could be so many things that influence that one day you go sampling and you have 30, and the next day you go sampling and you have, I don't know, something above 70, and it was because something happened there. So all of that is shown here, and that's something that I struggle a little bit to work with the variability of that, to see how can I get rid of all of this huge point. And one of the things that it's been done, that's why I use geometric means, because it helps to kind of take that down, because if you use the regular arithmetic mean, just huge.
So it's just natural variability in the measurements, it's not a data problem?
Natural, I don't want to say natural specifically because of all of the other influence, but yeah, that's the idea.
But this is the variability you would expect to see, is what I'm.
That's what I got from the data, yeah.
But you're looking
There.
at 10 years of data here, right?
This is about 10, 11 years of data, yeah.
So that
Yeah.
has to be geometric means for 10 years of
Gotcha,
data.
okay, maybe I just missed that.
David?
So I had a question about part 3.
Mm-hmm.
You had mentioned that there was a subset of the younger than 24 age group of 5 and younger.
Mm-hmm.
Analyze those separately, or did you keep the 5 and under in the 24 group?
They were together in the 24 because I consider them as well as to be exposed to the virus, because they still go outside, parents, they play outside, I consider that. So
Did you check to see if you removed them from that group and did it from 5 to 24, if it would change your results that much?
I actually did that check, but that would be good to look into, but I didn't check into that. You had your hand first. Yeah.
Thank you. I wonder, from your research, if you have an opinion on whether the concentration of bathers at these beaches could affect the incidence of health-related reported issues, or if you don't have an opinion, is it possible to include that as a factor in the study?
That's a really good question. That's something that I kind of wanted to look into in terms of the amount of people going into the beach. I've talked to other colleagues, and they've looked into something very similar. And we shed a lot of stuff when we go into the beach, and it could be very, very nasty. So I would assume that when you have more people, like summertime here in Florida, there's more going on, and resuspending everything. But there's the fact that we still have a lot of sun, it's warmer, so there are many confounding factors there. But still, I would think that concentration might go up.
In your last chapter, you had mean sea level
Mhm.
variable. Can you elaborate on how mean sea level would impact what you said?
Yeah. I don't know if I have it here, because that's one of the ones that I had to kick out because of time. But In terms of mean sea level, what I'm looking at is, I got the data from from Hawaii, all of the buoys, and when you have lower mean sea level, what we think is that there's less pressure on land. So if we have other discharges or runoff, it just goes into land, and we have a peak, assuming that all of it's coming from land is with poop. But when you have higher sea level, it may be more like you're just pushing it more into land and just kind of stop that, and we get lower concentration of the bacteria. And this is what I saw from my data, and I think something was done in Miami that they saw the same relationship with lower mean sea level. We got higher peaks in bacteria, probably because of that discharge or the backwash of the waves, just high energy, resuspending everything. Higher mean sea level, just pushing everything or diluting everything in the water. Does that make sense? Yeah. There we go.
Abdiel, can you go to that last view showing the predictive model output, the WO values?
For which one? It doesn't matter which one.
I'm
This
just
is.
trying to understand how to interpret the WO or the predictive
That?
output values. Yeah, so when it's negative, it means what?
So, I kind of focus mostly in the magnitude of that influence, whether it's positive or negative. I didn't look too much into that. When I go back and I'm talking with the people that worked the model originally, the way it was coded, it's binary coding to identify exceedances or no exceedances. That binary coding can be a little bit confusing because the 1 and 0 were put the other way around. So when you see a negative influence or positive influence, it needs to be interpreted in that sense with the binary coding. And some of them might look switch, but it's more because of the coding, how it was done, and also because when you're training all of these models, let's say for dengue fever, you're training with years that barely have any cases. So if I'm going to make a prediction, it might think that it should be down here, but then it's all the way up here because other things happening with the virus. So you might think that that could be a negative correlation, or all the way around, a positive correlation. So the weights can be a little bit tricky to be able to identify them. So that's why I mostly talk about the magnitude of that influence. It doesn't matter if it's positive or negative, they're influencing what's going on. Does that answer your question?
Yeah, because I was a little confused when I saw the values for number of cases in the previous year.
Mm-hmm.
So that was kind of confusing.
Yeah, and it's because of that coding mistake there, because we kind of flip it up, and then again, because dengue fever, because it has different peaks every year. So if I predict something low and it's high or it's all the way around, it goes more into understanding what's going on with the virus and in that area in terms of the environmental parameters. And then the model is just giving me those numbers. Good. Hey.
Great presentation.
Thank you.
I think yes, it's very important because where things have to go is nowcasting and forecasting.
Mhm.
But I'm trying to figure out how much weight does the biology have in your models? And I think where I'm going with this is new virus being the mosquito, right? It's
Mhm.
one species that we know transmits a lot of viruses. How much do I need to know of the biology of that virus to be able to predict it? Or if I'm really already at models for dengue, for example, which is the same vector, does the vector have more weight on those predictions? Do you think your models follow more the behavior of the vector because they correlate with temperature, or if they're more active or not active, or do I need to know
I think
more about the virus itself?
I think it would be good to know more about the virus and how the virus is behaving or mutating or whatever is going on with the virus. And not only that, but also we need to know the population immunity. Because it doesn't matter if we know everything about the mosquito or everything like that. If we have a population that had never been exposed to the virus, it's just going to peak. But like everything else, it's just going to go down, and they're going to develop that immunity. But we live in a world that we keep traveling and going to many places. So I think it's most important to know that population movement and human immune system and how that works in that specific area for better predictions. Because the virus is going to be there, and it's still important to know the virus mutations and all of that, but our immunity is going to play an important role of whether or not we have an epidemic, an outbreak. And we saw that with chikungunya back in 2014, and Zika virus, all of a sudden everyone got that.
So related to that, when you did your
Like Karina should say she's Karina.
Oh, to say who you are. That's Ricardo Zurrieta. He's one of my committee members. Sorry.
just related to for your models, was that, like, sorry if I missed it, if you want to. Hi, I'm Laureano-Rosario. Thank you for fast. For your models, did you distinguish the serotypes? So, because you were talking, there's 4 different serotypes. So when you did your predictions, did you get better predictions for different serotypes, or it was all like dengue case and that was it?
I didn't have the data for the serotypes.
Okay.
When you get the data, usually it's very few cases that they do the serotype analysis, and you just get an idea, 2014 we have serotypes 1 and 2 in this state, and in this other state we had 3, and you get an idea which serotype is circulating. I actually didn't add that into my models, which probably is going to be really helpful to be able to do that.
Sorry, we don't love you. And you also know you get, depending, depending on how many questions you get, that's how interesting your presentation is.
Really?
So, and also I'm Maria Vega, but I'm going to ask a question that was handed down to me, but I think it's important.
Handed down to you? What?
So, date, you use date as one of your variables,
Mhm.
I think in your 3rd chapter.
For dengue, yes.
And the question is, like literally the question is, wouldn't this be considered a super variable? Like it takes into account temperature, like sea surface temperature, precipitation, which I think this question is related to the chamber system too.
You mean like they being correlated with increased temperature and all of that?
Dates,
Yeah.
right? So
Mhm. Mhm.
why would you use something like date?
Actually, the question was for me. I'm Gabriel Quiles. Yeah, if it would be considered a super, but I call it super variable, meaning that
I understood that, don't worry.
yeah, that it will sum the effect of all seasonal parameters like temperature and others.
I could see that happening. The way date was put in the model is just a continuous number from, let's say, just 1 to 365. Just to give you an idea. And within that, you're still going to see an increase and decrease in sea surface temperature or air temperature. So it might happen. I didn't check without date, but I don't know how much of a difference it's going to do in terms of the model outcome. Just, I think 2 of the model identify date as the most important, and that still is kind of expected because of the cyclic pattern of dengue. Does that answer your question? Thank you.
Other questions from the audience? All right, let's thank Abdiel again.